Hello.
Hi.
Anybody know who's the host of the meeting? Because I can't record. I think Aaron can't make it. I'm trying to see if I can record it. Oh, somebody's recording.
I'm not sure if it was put on recording while I entered, so I'm not sure who put that on, but I believe it must have been Aaron at some time.
Yeah, maybe it's a feature of Zoom where you can actually have automatic recording. Sounds cool. I know there's, let me check. Jeremy, is Jeremy here on? Okay. Okay, we're gonna wait a few more minutes and see who joins in. Like, oh, 30 past 1. So we have some usual people. Hi everyone. Is anybody new here that wants to present themselves? Be nice so we can get to know you all.
Yeah, I can go. Hi, I'm Ankit. Can you guys hear me?
Yes.
Yeah, I'm Ankit. I work at LinkedIn. I've been in the Golang channel where there are a lot of folks, and I think we have a very vibrant community. I just play around with Go on like my own time, but now we have started to kind of use it in our team. So it's great to like have such a good community. Yeah, happy to be here. I've been listening to like talks on YouTube for this study group. I thought I'll join this time.
Cool. So Aaron can't make it. He had appendicitis or something like that. His appendix got removed. So
it's called
I guess now it's out there.
Yeah.
Now the whole world knows. So I know Jeremy was maybe supposed to log in and show how sorry about that. Show how he would like go about debugging a bug in the kubelet controller in the Kubernetes project, but I guess he hasn't shown up. And I'm wondering if Caroline is going to show up. Apparently she has an announcement. So we'll wait for that. Oh, there's somebody who's saying hello from Jenna. Oh, Nokia, the indestructible phones. Cool. And yeah, so I'm a little bit out of ideas of what to show. I don't know if Carrie, I can put you on the spot. and show another of your great tools. If not, I guess I could show how I go about doing. I don't know.
I'll take a little bit of time asking for help while we wait for the person who's going to present today. I am really interested in non-locking data structures and queues and stuff like that. So I've got a bunch of experiments on my GitHub. If anyone else is interested in that, hit me up in chat, because I'd like to, chat about some of those things. If you want to talk about it, that's great, and we can share some ideas. But just figure a call out to anyone else who's like-minded.
Yeah, we did have a good conversation the other day about the queue and the channels. So anyway, it was fun.
Yeah.
Do you have a little something that you can show, or
well,
out of the box?
Out of the box? I mean, I've got plenty of stuff out of the box I can show, but it depends on what people want to see. But yeah, I have. Let me pull up something. I mentioned Gulf, but it's Gulf. We talked about GoDirWalk the other week. Gulf is just a very lightweight. It's exactly like Flag. So if you like Flag, but you just wish you could use 2 hyphens instead of 1 for command line options, give Gulf a try. It's a drop-in replacement with for Flag. I will paste its URI in the chat for people to take a look. But it's a nice little library for just drop in, replace Flag. It does not do all the other stuff like change how you write a CLI, which is a command line program, which is what I'm not a fan of. I like the lightweight approach to take my Flag. I just wish it had POSIX and GNU compliance. So that's what Gulf is. Go long Flag is what it stands for. So if you're interested in that, that's great. I also have, I don't know if anyone uses sync pools at all in your code, with the data structure called sync pool, sync.pool, especially if you use it for buffer pools. I've got another library that is faster, more efficient than sync pools for buffer bytes buffer structures. But we've used it extensively at my job for over a year now, but we tested it, we benchmarked it. It is more performant than, because it does, just like a GoDirWalk, there's a lot of stuff that edge cases that GoDirWalk does not take into account. GoBP or Go Buffer Pool goes ahead and it stops, it does a lot of things you want for a buffer pool, whereas sync pool is a little more generic for other stuff. So GoBP is a lot more efficient both in memory and CPU time. So those are pretty interesting. If those things interest you, then check them out. But yeah, just trying to.
Okay, I'm actually very interested in the. I've never really used sync pool, and for me, I would be really happy if you just showed a little example how like they work, or how you did the library. I don't know if it's possible.
Sure, I'm happy to do that. Let me open up a page and I'll share it with you guys.
Yeah, that would be perfect. Then if you also kind of tell what it can be used for, because I've read, I know it exists, but I have no clue in what's the reason for using it.
Sure, absolutely, that's fair. So let me let me do the share thing here. Invite.
Because I think a lot of time, like new Go developer and like myself too, we find channels and we're like, whoa, channels everything, and then we keep on going, and at some point you're like, oh man, I'm making way too many channels in my Go codes everywhere, and it
channels. Oh, go ahead. Sorry.
That's it. Like you come to a realization that channels are not the answer to everything. So
right.
and you have to know when to use them and when to use like a weight group and I guess sync pool. Like,
yeah. So let me give you an idea. Let's say a sync pool is great. We'll just talk about what a pool is, or it's a pool of resources, if you will. Let's say your program is like accepts web requests and it wants to churn on the data a little bit and build a response in a buffer, bytes.buffer structure, and then write it back out to the HTTP response writer. When you do that, the program that I was working on when I developed GoBP, it used to just allocate a new bytes buffer, which is completely fine. You know, the way it's like when you're first drafting a program, you pretty much want to just use those simple constructs. It would allocate a new bytes buffer on the fly, and it would turn around and use it and then throw it away. When the function exited, the garbage collector would pick it up and put it back in the pool. But there is a little bit of overhead with that. Not only one, you've got the garbage collector getting involved. Two, you are there's the memory behind a bytes buffer that also is getting reclaimed. So it's the data structure itself, which has pointers to other data structures. So I created GoBP. And then we ended up, sync pool came out afterwards. But when sync pool came out, we did some benchmarks, and this still does it better. What sync pool is a great pool that you can use concurrently in multiple Go routines. So let's say if you've got a HTTP microservice, your response handlers can use these sync pool, not what you see on the screen here. I should godoc.org sync pool, or just sync, and then we'll look at pool here. There we go. So you can use a pool structure in the sync package in order to dynamically allocate new items, but you don't just throw them away back to the garbage collector when you're done. You give them back to the sync pool when you don't need them anymore, and they sit there waiting for something else to want them. So it's a lot more efficient. Your garbage collector is not going to be used as much, and the interface is real simple. You have a get method on sync pool, which you create a sync pool. You define a function that is used to, here, let me click on the example. So can everyone read this, or let me expand the font size?
that's cool. Yeah, thanks.
Awesome. So at the program beginning, we create a sync pool, and you could use a new method, but you don't need to, which I love about how Go works. If you don't need to use a new method, you just define it, define the data structure. You create a sync pool, and it's got a new field, a data field, and that takes a function that the Go runtime will invoke or technically it's the library implementation. But the Go library sync implementation will invoke when it needs a new resource. So you define it and you say, hey, whenever you need a new thing because something calls get later on, here we got a buff pool we're going to call get. We want you to invoke this function, and it will return the item that we want to get. So in this new function, we want it to return a bytes buffer, specifically a pointer to a bytes buffer. And then that's how we define the buff pool. The buff pool has two methods. It's got a get method, which the get method, because the get method interface that it has always returns an empty interface response. You have to do a type assertion. That's what's here, not a type cast, but a type assertion. When you're saying get something from the buffer pool, and I promise you it is going to be a pointer to a bytes buffer. That's what the type assertion means. Then we're going to call, since we've type asserted it, now B, the data structure B, has all the type information that a bytes buffer would have, or specifically a pointer to a bytes buffer would have. And so we can call the reset method on the buffer. We can use it, create our response. In this case, the example is creating a log line, and then we're going to release that resource or put it back in the pool. I'm going to put that bytes buffer back in the pool right here. So you could think that in the fact that this is in the sync package is because it's implemented with concurrent programming safety in mind. So it will turn around and you can have many functions in your code concurrently calling this log function, because it is going to use a concurrency protected buffer pool, or this buffer pool data variable, which is the sync pool data structure. Okay, so having that in mind and having this example in mind, if you went ahead and benchmark this, you could take a look and see how well it performs. And if you look at number of allocations that's doing you can benchmark it under high concurrency, low concurrency. It's great. The implementation is very, very good, but it's a generic implementation for a generic object. The generic object being anything, just a sync pool. It doesn't know what you're storing in it. It does not know that you're using a bytes buffer structure. So there are some optimizations we can take, and we can actually get better performance if we know we're using a bytes buffer, if we use something that actually has been designed with a bytes buffer in mind. So let's take a look. This is the GoBP package. It's a Go library for using a pool, also known as a free list of bytes buffers. And there's a little bit of background. There's a couple of blog posts and articles about different approaches to this. And that's what inspired me to write this. I saw someone else doing this, and I thought that there were some optimizations that could be made in their code, because, and I was using a method already. And so I just went ahead and took my chunk of code, made it a library, and put it out there and referenced the original article. Okay. So description, this library provides a pool of buffers to your code, so you can use them concurrently. Use it very much like the example we saw earlier. We create a buffer pool, and then we get a buffer from it. Now you don't have to do any type assertions, because in this case, this library knows, and it's only exclusively for bytes buffers, byte buffer data structures. So we use it, and then we turn around and put it back in when we're done. Here's a more complex example with concurrency, all right? We're gonna do some math random stuff just for a silly example. We're gonna import the code. There's a couple of parameters. Notice that, I'm gonna scroll back down. Notice that you can just initialize a GoBP without any configuration options. However, if you want to tune it, you can. There's 3 tuning handles, and they're well documented in GoDoc. There's a buff size init, a buff size max, and a pool size max. Buff size init is how big do you want it to create a new buffer when it runs out of resources and you want it to create a new buffer. Buff size max is when it gets a buffer back from you. Sometimes if you've got let's say an HTTP handler, response handler, and you are building a response, you're like, okay, my normal responses are less than 32K. I'm going to use that for buff size init. But if you ever have a response, it's a huge payload, and that response is like 64K or maybe a couple of megabytes, you don't want all that allocated space to be sitting there, never collected by the garbage collector. So buff size max is a limit that you place on the buffer size, a max limit you place on the buffer size when it's returned to the sync pool. So if you put a max on here, and these are simplistic examples, but if you put a buff size max of, well, in this case, it's 17 kilobytes, which is kind of silly. Maybe I need to change the example. It's not very informative. But if you put something that was 17 megabytes in this example, when you get your buffer back and it's greater than or equal to 17 kilobytes, the pool will drop it on the floor and allow the garbage collector to reclaim it. So if you have one of those HTTP handlers and it dynamically creates a response, a mega response that's like a megabyte or 2 megabytes, or heaven forbid, a gigabyte response, the pool won't hold on to that memory forever. Even though the pool, you might not use that memory again, the underlying array would still have it, and you don't want that to happen. So this I felt is a shortcoming of SyncPool because it doesn't know what you're handling. SyncPool does not know that we're handling buffers, so it doesn't have any capability to handle the logic of, you get a really big blob back, let's throw it on the floor and let the garbage collector have it, because we don't want your memory footprint to continue to increase. Because if your backing array is really big, even if you never use that again in the life of the program, that backing array is going to keep its size. Okay, and then pool size max is, I only want maximum of 100 items in this pool. Anything else, then we don't worry about it. And why that will come into play a little bit later. Okay, here I've got an example where we optionally fill in the pool with the pre-allocated buffer, and I'm just setting us up and saying, hey, let's put a bunch of things into the pool to start us out. All right, and all I do is I run through pool size times, let's say 100 times, and I put something in there, and I pre-initialize the buffer. I don't need to do any of this. Then we run some concurrency tests. This is just a silly example, but the bottom line is we're going to run this thing a bunch of times. And this function is going to run concurrently, but it's also in a loop. All right, it's a grab buffer and use it. In this example, we have a function like all resources obtained from a pool. If you fail to release it, you result in a resource leak. So you grab a new bytes buffer, you defer, put it back, and then you run your function as normal. And when you exit, the resource gets put back into the buffer. Here's an example where we say, okay, we're going to randomly make the response larger than, it's a silly example, but we're going to loop through a bunch of times and fill the bytes buffer with a bunch of random bytes. But periodically, randomly, we're going to make it bigger just to see how the pool handles it. And it drops it on the floor when it gets it. Okay, you can, if you check out this code, feel free to run the benchmarks on it. It'll benchmark it against some other libraries out there that I found and the SyncPool method. And you can see for yourself if this is worth your attention or not. Maybe you don't need a bytes buffer and I'm wasting your time. Let's look at the implementation. So, let's go back. So I'm comparing it to, so there's a benchmark test. There's a couple of different ways of implementing this. Here I do it with a channel and bspool test. And the main implementation's right here. Okay, and I promise you there'd be documentation. If you go to GoDoc, this is what you'll see. It describes what these three tuning parameters do. Here's a meat. When we get a new bytes buffer, I do a lock on the data structure. And so this is now into Go coding a little bit. Let's look at the data structure real quick. It's just those three parameters, a data field called free, which is a slice of pointers to bytes buffers, and a lock, which is a mutex. And I use a mutex here. And that's a different conversation about choosing different concurrency safe data structures. They're not evil. I think you just need to use the right tool for the job. In this case, benchmarks show that this is the right tool. It might not be the right tool for all situations. It's definitely not. So there's a critical point where we need to lock the data structure so nothing else can use it and cause a race condition. But take a look at how I lock it. I lock it so I can now check whether or not there are any items in the free list. If the length is 0, then we immediately unlock that. I don't need to wait to unlock until line 47. I just wanted to guard this data check right here. Now, having said that, if this were a different type of variable, I would probably using an atomic uint 16 or not 16, sorry, uint 32 or uint 64. But in this case, we're looking at the length of a slice, and we don't have, unless I did some unsafe items, actually, it would never be safe. We're not controlling that data structure, so we're checking the length, we have to lock it. So I check that one value, and then I immediately unlock it if it's 0, okay? At this point, if the user configured the pool without specifying a size, we just return a brand new bytes buffer, which is going to use its default size, whatever the standard library says. I think it's 4K, but it doesn't matter. If the user did specify size, we initialize it and send it back. Notice that we're not touching any other data structure or data member of the pool structure at all. We only check whether or not it's an empty list. And if it is empty, we can immediately exit, because the rest of the code path is just returns, and we're not modifying or checking any values in the data structure that we're protecting, the pool data structure. We're not modifying or checking anything else, so we can release the lock right away. So that really helps us there. Now, if there was at least one item in the free list, line 47 is not unlock it. We still want to keep it locked until we execute the next 2 lines. Okay, so here I immediately unlock it. I can release that resource and eliminate contention, but for the slow case, or the more common case, sadly, there's going to be items in the bytes pool, the free list of bytes buffers. So we're just going to declare a variable. We're going to grab the first one off the list. That's what that does. It does a shift if you are familiar with Perl or even Bash programming. It grabs the first one off the list, throws it into the BB variable, and sets the list equal to the remainder of the list after the first one has been removed. At that point, we no longer need to unlock or we no longer need to modify any data structure, pool data structure variable. So we unlock and then return that pointer to the bytes buffer that we got off the list. So a couple of you might be saying, well, Carrick, why don't you just put a line 39 defer unlock here, and then don't worry about forgetting line 41 or 51. I absolutely could have done that, definitely. It would have been fine, but then first reason is, while defers are great and awesome, once you hone a program and once it's tested and you have test code in there to make sure you don't have a memory leak, sometimes you can improve performance if you remove all the defers from a function. I won't say that's a recommendation. I would say that's my observation. So for very small functions, I might eliminate the defers and just manually defer when I know it's safe. Okay, and that's what I've done. Also, too, if there was no items on the free list, then there's no reason to hold on to the lock until this all completes. We can release it and improve concurrency a little bit. That's why. Okay, this is a small library. One more method on this data structure. We're done. Put's going to take that from your code and throw back in the bytes pool for other coroutine or Go routines to use. But it doesn't always do it. And let's take a look and see when we do it. So first of all, if we're not obtaining a lock right away on line 61, we don't obtain a lock to line 65. Let's talk about why. On line 61, we check to see if the user specified a maximum byte size. So if they said the byte size maximum is 16K, then we need to actually check it. But if the byte size was 0, we can ignore this whole clause because there's no maximum. So this guard on line 61 says if they specified a max byte size and if the capacity of that bytes buffer is greater than the max size, then we're just going to immediately return. And what happens is we drop that buffer on the floor. BB is no longer referenced at this point, and the garbage, simplified example, and the garbage collector will pick it up next time it makes a run. Okay, so at that point, we know that it's a candidate. If the buffer is not too big to be put back in the pool, we know that we need to now lock some data structures to check the length of the pool. And before we can do that, for concurrency safety, we have to lock the data structure. So we put ourselves in the mutex. And we do a very similar check here. If the user specified a max pool size and the length of the free list is equal to the pool size. So let's say the user specified there's a max of 100 items and we already have 100 items in there, then we immediately unlock and we unlock to the mutex, and then we return, and that drops the buffer on the floor. So at this point, we don't need to care. We just let the garbage collector pick up the buffer. If the users did not specify a max pool size, let's say pool size max was equal to 0, then we skip this whole chunk. And the pool size can actually get larger, and we can have more things thrown into the pool than, or there's no max limit to the number of items. Okay, line 72 through 75 is the last bit. We know we need to store the item back in the pool. Before we store it, we're gonna call reset on the bytes buffer. So that way you don't have to reset it when you get it. The library knows that you're dealing with bytes buffers, and it will reset it for you. And the beautiful part is, well, yeah, whatever. I'll relegate. I was going to make a comment about that. Why do it here and not in get? But that's a different topic. Okay, now we've reset it. We're going to append it to the free list, and then we unlock the mutex, allowing other functions, either gets or puts, that were waiting for that mutex to proceed. And that's the entire library. Let's go ahead and, if you'd like, I'm happy to run a benchmark. I have to change what I'm sharing. So let me stop share and open up GoBT. Let me open up Git stash. Not sure what I was doing there. Oh, okay. And let me share my Emacs terminal with you guys. Okay. All right. Okay. Oh. Let me go grab a copy of the command again. There we go. So we're going to run a test, benchmarks, tags bench. Okay, what this is under low concurrency and high concurrency. Different ways of creating byte pools or buffer pools. And this is on my Mac, which is also doing a bunch of other stuff. I would not consider this definitive, but definitely run the benchmarks on your computer and even modify the benchmarks on your computer before you turn around and use this. So there's benchmark examples right here in the code with a framework that you can add a different benchmark library. So you can add that and benchmark that too. And basically, I make them all look like this. I make all the different libraries I'm benchmarking against have a get and a put. And no pool is actually just something that churns and no pool just returns a new bytes buffer each time. So it's GC heavy, but at this point, you don't have to worry about any concurrency primitives holding you back. Here's sync pool, which I discussed earlier. This just wraps sync pool in a way, the exact way that they showed us in their example. And then I've got a benchmark runner called exercise, which it's going to turn around and write a bunch of bytes. And then I've got bench low and high. Bench low and high will run a low concurrency benchmark and a high concurrency benchmark. Low concurrency, it runs it using the testing framework's run parallel command or method. So it allows you to, it takes a look at how many processors you have and determines how much parallelism to use in your tests. High concurrency, I manually use 100 times the number of CPUs you have, and that's how many Go routines we're going to run concurrently. And we're just going to run that exercise. So that all the stuff above is setting up for the test, and then all the stuff below here is just going to run it. A Go BP, a Go pool, which is a different data structure. No pool, which is, again, no, you're not doing pools, you're just heavy GC, and then sync pool. Okay, going back here, we can look at it. So remember, run tests on your machine and even modify those tests to take a look and see, because benchmarks without context are not, don't mean much. But if you actually put your data types in here and your usage types in here, you're going to actually see have much more informative benchmark numbers. So I did the work. I wrote the benchmark framework. You just got to update a few methods, and you can run this. You see Go BP under low is 25 milliseconds under low concurrency. Which is only slightly faster than Go pool, which is good, because actually the Go pool library has been updated quite a bit since I wrote this to do a lot of the things that we're doing. You see that it's actually even faster. Go BP is faster than running no pool at all. So there's no mutex at all in the no pool example, and Go BP is actually faster than using no pool. The thing that's holding you back and making this slow is because now you're forcing the runtime to allocate more memory every single time. Now it's smart, and it's going to allocate memory from a chunk of previously unallocated memory, and that has the same size, and that's how the runtime memory allocator works. It's very smart, but the fastest way to do something is not to do it at all. And you can see here that if you actually have if you don't have to allocate that memory or turn it into the garbage collector, you're much better off. Here's using a sync pool. So again, this might not sound like it's that big of a deal. Who cares if it's only a few milliseconds? Well, maybe you don't care. But we do know that Go BP is more fast and it's more memory efficient than using a sync pool. So I recommend you use that. Here is a following another B spool, a different library, and using GoP with channels. So I've got channels in here because I wanted to implement the same logic, but instead of using a sync mutex to implement the pool structure, I'm actually going to use a channel. And I initialize the channel, and then I emit items from the channel when there's a get. So in this case, this is just a test file, so I'm not worried about the commented lines because it was just used for benchmarking comparisons. In this case, for the channel version, I learned this trick from Dave Cheney. He has an excellent blog post on on usage of channels, a couple of excellent blog posts. I definitely recommend. I'll link them in this channel after we're done. But when you select from a channel that has something available in it, you can return it right away. But if you have a default section, if there's nothing in that channel, it'll actually run the default section of the select, which is a really cool thing. So if there's nothing in the channel, I just use I just create a new one on the fly, which is similar to what the other method does that uses sync mutex. The put is very similar. I select from the channel. If I can put the extra bytes buffer in the channel, I do. And if I can't, it goes on the floor. No harm, no foul. It's just dropped. So that's the channel. And channel is less efficient than the sync mutex in this case. In both cases, high and low. Again, take a look at your high and low benchmarks. I think they're interesting to differentiate between a toy example that just has a few concurrent programs or processes running, or thousands or hundreds of concurrent Go routines running. The higher, depending on how your program is designed, if you only have a half a dozen or a couple of dozen Go routines that you plan on running, then that's what you should be benchmarking. But if you're designing some work scheduling algorithm, and that has like thousands of Go routines running, then you want to benchmark with thousands of Go routines to mimic the same behavior. Because sync mutex or all the synchronization primitives, some of them break down at different rates at higher levels of concurrency, which is why the whole notion of lock-free data structures and the 3 different types fascinate me. And so I've got a couple libraries I'm working on that to hopefully have a FIFO type queue that can be used with a little more performance than we see out of channel. Because in earlier examples, not of this algorithm, but a different program, benchmarks show, and actually that's there, and I want to talk about this. This is actually really cool. It's called GoSwarm. Here's a cool library called GoSwarm, and you can't see that, so I'm going to stop share and go back to sharing, and I'll stop here after I bring it up. GoSwarm. Okay, it's a Go stale while asynchronously revalidate memoization. What a terrible name, but it's what it does. So GoSwarm is a library for, it's like a memoizing cache, but it serves a stale while it it serves stale data while it asynchronously revalidates it. And it's definitely something to look into. Again, this is used heavily. It's been used heavily for years, and it's a nice little function. So if you've got stale data or there's an error on your source of truth, it will turn around and continue to serve that, but it revalidates that data. And then eventually it does have, it's got both a time to live and a time to expire. And after that time to expire, it will never serve that data. So you don't need to tweak it as much as I do, but there's a lot of tweaking things. And I'll like to talk about that sometime, but I should stop taking up everyone's time.
Thank you very much. That was very awesome. I have a little question is, how do you go about really identifying sort of quickly memory allocation everywhere that happens in
Absolutely. Sorry, I forgot to mention that. Let me go back and show you. If you go to the testing, actually I can more easily go here, Go doc testing, and I have this in examples, but memory, if you search for memory, okay, reset timer, we know that reset timer, we use this a lot. I'm sure you use this a lot in your benchmark test where you reset the timer after you do some setup. But the function right above it is report Alex. If your method
we don't see your screen.
Oh, you don't. Okay, so sorry. I'm going to share that. I thought I had set it back up. Okay, report Alex right here. If you call that in your benchmark, it will report to you when you run your test all the allocations it made. So that's nice if you want some benchmarks to report all the memory allocations and others to not report the memory allocations. But there's also a Go test I need to find it though, because I can't remember. If anyone else knows, please. Report Alex, Alec. No, bench mem. There we go. Sorry. Find bench mem. Okay. If you call test with a -bench mem, it will also report the allocations. I'll run that real quick. I'll share my Emacs screen with you guys. I'm not sure where it went. Oh, there it is. Okay, let's go back to where I ran the test. And I'm going to test. Go test minus b bench equals dot, tags equals bench. Tags equals bench is for this particular library. If you give it -bench mem and run it, you're going to get a lot more information on the screen, and it's going to show you how many allocations were made and break it down in 2 different columns. Okay, In this case, you've got the first one, there's 16 bytes allocated per operation, but it says 0 allocations were made, 0 calls to like a memory allocation, probably because I forgot to do a reset timer in there. But you could see how many bytes and how many calls to the runtime to allocate new memory were made in each example. And you can see that the no pool high is making 1,627 allocations, allocating a total of 13 megabytes. Whereas the Go BP high is only making 330 allocations for about 100 megabytes. So you can see that statistic as well. Let's go back into the test code right here. And, oh, I do call reset timer. I call reset timer in both places. So I'm not sure why it's doing that, but I'm going to chalk that up to fuzzy area and hand wavy stuff. Did I answer your question though?
Yes, thank you. And I have one quick one. If anybody has another question they want to ask.
Oh, somebody, Dale Wiss said, I'm surprised channels underperform mutexes. Remember how channels are amazing, but they're implemented with the same fundamental concept that mutexes are implemented with. So they're a higher level construct on top of mutexes. So naturally, they're going to underperform a mutex because you could, I'm lying a little bit, but channels are built out of mutexes. And again, that's a slight lie. If you dive into the runtime, you'll see that channels are a lot more complicated than a simple mutex. They're really elegantly created. And actually, mutexes are also not simple atomics either. There's a lot of smarts put into those runtime implementations, but for the simple sake of saying channels are an abstraction on top of mutexes, again, I'm lying a little bit, that helps understand why channels would underperform. Channels are meant to be easy and help you make bug-free code. Mutexes were not. Mutexes are made for raw synchronization primitive, and that's what they're used for.
And am I wrong if I think I read somewhere that with channels you do have memory allocation that is done per channel that you're having versus mutex? It's just a lock. It's more. I don't know if I expressed myself well.
Yes, just like you know, when you reset a bytes buffer, when you create not the library I just did, but if you use a normal bytes buffer data structure from the standard library, there's the data structure itself, and it's got a couple of data fields that it needs, but it also has pointers to your actual memory, the actual slice that contains the bytes. And when you think about it, the slice itself is also two integers and a pointer to the actual place in the actual physical place where the memory or the underlying bytes are stored. So that's going to happen a lot. So channels, because they're built, if you will, on top, they have a lot more complexity than a simple mutex. And mutex is very lightweight. It's not just a simple atomic that's being modified. It is actually a very smart atomic or additional data in order to prevent or mitigate the effects of starvation. There's a couple of cool things in the implementation of the mutex that allow us high-level people to use them and not have to worry as much about thread starvation and those things that actually worry people at night that we don't have to worry about because a lot of that smarts was put in there. Channels, more so. You're going to have a lot more complexity that's needed. So you need to allocate storage or the runtime will allocate storage to hold on to those data fields that the runtime needs in order to manipulate these channels on your behalf.
Cool. Thank you very, very much for saving the Go Study group. And that was super informative and actually answers a lot of questions I think that a lot of I have anyway, in terms of mutex channels and how to organize some of the codes that we try to write. Any other questions?
One thing I'd ask, Carrick, is where do you have any particularly interesting places that you've used either GoBP or GoSwarm?
Yeah, I use them a lot. I like almost every time I build up a web service that's going to answer response, I'm using GoBP in order to build that response. I do have that's another deviation, another library I've got that's for HTTP. It's a lightweight HTTP middleware that does logging that has minimal allocations, but and a parser and a compiler and stuff. But that's really sounds complex, but it's not really. But so I use GoP every single time I have an instance where I want to have a bytes buffer and and by a service that's answering queries, I'm going to turn around and create a pool, just like you saw here. I'm going to create a pool and get and put the bytes buffer back in the pool at the end, and the performance is there. I use it a lot at my in my open source projects. I've used it a lot at my work because it's licensed either MIT or BSD2 clause. I think pretty much every single library I have is out there it's licensed like that. So I use GoBP extensively. I also use GoSwarm extensively. GoSwarm was like I needed to cache something. Like I have a service, I was creating a service and it had a source of truth that it needed to pulse and ask questions to. And unfortunately that source of truth was not reliable. In other words, well, one thing, it couldn't handle the load. So I wanted to have some sort of TTL that I would wrap around it. The initial version was pretty good because it would just hold on to the data and, expire it later on. GoSwarm actually became more important when that service started dying, and I was getting woken up not my service, but the source of truth was dying, and I was woken up in the middle of the night, and I'm like, okay, the service I wrote is a critical piece of infrastructure, and if it can't talk to that, we have a big problem. I had a 4-hour TTE, or time to expire, in there at the time, and that's since been up to 12 hours. Because if that underlying service dies, I want to be able to handle a 12-hour outage from that and have my service still running. The cool thing is with, you can use GoSwarm like a key value store, but it's fine. That's what it does. But it's a concurrency safe key value store. And I can go into how I came up with that. It's like a map, but it's concurrency safe. And I did this years ago, back before we had concurrency safe maps in the runtime. I did it, I want to say 4 some years ago, and I have a whole library that benchmarks, I'm going to paste it in here. It benchmarks all the different ways, github.com, Carrick, Congo map, concurrency Go map. And Congo map is a benchmark of, I think, 3 or 4 different ways to make concurrency safe maps in Go. That's all it is. It actually is a great library if you want to use one of them, but it's really a benchmark example. Run it on your system, both on your servers, on your Mac, and run the benchmarks and see how well the different concurrency primitives work in Go. And you'll see that an operation with a channel takes 1,300, this one particular operation for a channel takes 1,300 nanoseconds, whereas an operation with a sync mutex, it takes about 250. And if you do a 2-level map, which is a different data structure, which I end up using, it takes about 180 nanoseconds. So it's much faster. And again, this doesn't matter for a little teeny project, but if you're trying to build services that are fast, I don't recommend Congo map. It's fast, but I would recommend GoSwarm. GoSwarm is definitely, I'll just paste that in here for reference because I mentioned it and I didn't type it. GoSwarm. So GoSwarm, what it does is you can say, hey, here's my source of truth and here's a lookup function. So the first time a query comes in, it's going to pause whoever's asking that function is going to pause. It's going to block temporarily while it goes and queries the source of truth. That might take a couple of milliseconds. It gets a reply back and hands it off to the client. Now, every single time another Go routine comes in and requests the same question, naturally, it's going to give it back right away. It's very fast, on the order of a couple of hundred less than 200 nanoseconds. However, if it ever gets a query for something and the time to live has passed, it's considered stale. It still serves it off right away, but that it enqueues a job, it smartly enqueues a job. If no other job for this particular data item is in the queue, it'll enqueue a job to ask the source of truth to update it, just like Nginx does. If you're doing like a Squid proxy, it can also be configured to do this too. It can serve stale data while it's revalidating. And the next item is it serves a stale data if there's an error. So let's say your source of truth went down. You know, the last time you asked this question of the source of truth, it told you 5 is the answer. It'll keep serving 5s while your source of truth is giving you errors because that service is dead. Does that make sense?
Yeah.
So
I've used a similar pattern. Oh, sorry, go ahead.
No, go ahead, please.
I was just saying I've used a similar pattern sort of manually before, but I haven't seen it so elegantly wrapped in a library. So that's going to be my go-to for these kind of things.
Cool. So I want to clarify, you said pattern, not patent. I hope I didn't use your patented code.
Definitely pattern.
It is, and it's meant to be, it's meant to be useful in not just the circumstance I used it, but in other circumstances as well. So I'm happy to talk about Ghost Swarm. I think that's pretty cool. And we got 1 minute warning. So any other questions?
Awesome. Thank you very much. That was great. And I think I'm going to go check out that Ghost Swarm, because I'm actually doing pretty much the same thing, but in with Nginx for one of my service. So maybe you can move it to Go and be happy.
Yeah, we used to have Nginx wrapping a lot of stuff, and there's no reason, if you've got a high performant, binary runtime that can handle it.
Yeah. Cool. And I think we're pretty much out of time. I wanted to do like a little bit like Go Time, do a shout out to free software thing. I'm going to do mine really quickly because I've noticed this really cool the Flatman Searcher, which is written in Go, alternative to H8, the Silver Searcher, or behaves like hot, and it's actually pretty awesome. And if you have any more links, you got about like 3, maybe 1 minute, 2 minutes to post it in. If you want to share one of Go library that you think is awesome and open source. Anything, we can all share Carrick's GitHub account and be really happy, but
I totally did not mean to monopolize this time. I was just trying to
No, it's okay. I'm really happy you did, because I had a crappy example, but I'm fairly new to Go myself, and I'm learning a lot of things. So my plan B was, show how to do table testing with the, because it's one of the first thing once you start coding, you need to do sort of, I like TDD right off the bat with my project. So, and table testing with the Go standard library, it's really easy and fun. So you don't need any external tool to do the jobs on small projects or library or package. Okay, I guess I'll call it adjourn. I guess so. So thank you, everyone. Thank you, Carrick, again for a great demo, and hopefully we'll have time another time for the Swarm and maybe put it in action. And so thank you. Thank you, everyone.
Are we doing one next week with GopherCon?
I have no idea. I'm not making it to GopherCon, unfortunately, but I think Aaron, he's going to be at GopherCon, so I think Caroline was supposed to announce something about it that would be a meetup, I believe. So I'm not sure. I don't think it's going to happen next week. But let's say pretend it's happening. So because I realize I'm saying something that I have no idea I'm saying what I'm saying. So pretend it's happening, and we'll see.
Or periscope in or something, or zoom in and shout out from our booth if necessary.
Yeah.
Yeah, and we can also update the information on Slack if it's happening or not. So
Yeah, I'll ask Aaron, and I'll post it on the Go Study Group Slack channel. And anyone who's going to GopherCon? Who's the lucky ones? Who are the lucky ones? Not a lot of people in here.
it's a little bit too far away.
Yeah, same here. It's the poor man Go Study Group.
Yeah. So if it was a little bit closer, maybe a few thousand miles or so, then
I wish we had those robots where you could go around. I missed the last GopherCon. It's actually going to be my first GopherCon, so I wish we had those disembodied robots you could sort of drive around and meet people.
Yeah.
That would be cool.
But it's also really nice that more or less all the talks are recorded, because I noticed that, for example, the Gotham Go was. So I watched that last week, and so it's kind of amazing that they put that out free for the rest of us to watch later on.
I think it's really important.
I think so. I think the Go community has been very embracing of like any newcomers and thing. So yes. Okay, GopherCon London was 3 weeks ago, I guess. Yeah.
Yeah, and it's also happening a small one in Stockholm at the beginning of October, October 6th, I think. So I think it's more or less the first one in Scandinavia, if you don't count in the one in Iceland this spring.
Cool.
So it's starting to happen here as well, because I hope Go will be a little bit more popular around here, but I think time will help.
Yeah. All right. Thank you, everyone.
Okay. Bye-bye.
Have a good day.
Bye. Thank you.
Yeah.